Welcome to Dreamtime Science, where curiosity meets tranquility and knowledge flows like a gentle stream. Here we explore the wonders of our universe at a pace that soothes the mind. You know, I've been thinking about how something as simple as a puddle of chemicals could, over time, become the incredible variety of life we see today. There's something remarkable about the idea that life might have started from things that weren't alive at all, almost like the universe quietly teaching itself how to grow. I can't wait to share some of the surprising ways scientists imagine this first spark of life might have flickered into being. If you find peace in these nocturnal discoveries, consider becoming a regular visitor to our quiet corner of science. Share in the comments what topic you'd love to dream about next. First, let's create the perfect space for learning. Cocoon yourself in comfort, release any lingering tension, and let your breath become soft and steady. Somewhere in the velvet silence between stars, in the hush that precedes all stories, there exists a question as old as wonder itself. How did life begin? The query glimmers at the heart of every myth, every scientific pursuit, every whispered speculation across the ages. It is a question that circles us, ancient and unyielding, woven into the very fabric of our collective curiosity. Tonight, as you settle beneath the gentle hush of the dark, let us drift together through the earliest dreams and imaginings of life's origins, a cosmic prelude where science and story first intertwine. For as long as humans have gazed into the night, tracing patterns among the cold fires of distant suns, we have spun stories, tales in which life was conjured by divine will, seeded by travelers from the stars, or awoken by the alchemy of earth and sky. In these tales, the unknown is a canvas, and every culture, every era, paints its own vision of life's first awakening. Consider how the ancients filled the void with narrative. To the Sumerians, the gods shaped humanity from clay, breathing purpose into inert matter. In Egypt, life arose from primordial waters, a lotus blooming on the surface of the endless flood. The Greeks told of Prometheus, who sculpted humans from mud and gifted them the divine spark of consciousness. These stories, fantastical and poetic, are not merely relics of imagination. They are the earliest attempts to grasp the profound divide between living and non-living, to understand how something as intricate as a fern, a fish, or a human might spring from the lifeless dust. As centuries passed, the tapestry of origin myths grew richer. In medieval Europe, legends whispered of spontaneous generation, frogs budding from mud, maggots springing forth from rotting meat, mice assembling themselves from piles of grain and rags. To those who observe the world with keen but untrained eyes, the distinction between the living and the non-living was mutable, porous, and mysterious. It seemed plausible that life could flicker into being wherever the right conditions gathered, like fire from a strike of flint. With the rise of science, the question did not fade. It only grew more profound. The age of enlightenment brought with it a new kind of curiosity, one that sought to peel back the layers of superstition and peer into the mechanisms beneath. Yet even as microscopes revealed the teeming world of cells and microbes, the leap from non-living to living remained as dizzying as ever. Scientists debated, sometimes fiercely, whether life could indeed arise spontaneously from matter, or whether it always required a parent, a seed, a spark, borrowed from what had already come alive. It is here, in the slow dawn of scientific thought, that popular perceptions began to shift but not to settle. The 19th century shimmered with bold speculation. The chemist Friedrich Wöhler's synthesis of urea, a compound once thought to be the exclusive product of living things from simple chemicals in the lab, hinted at unsettling possibilities. Perhaps, some reasoned, there was no impenetrable wall between the animate and the inanimate. Perhaps, given the right ingredients and the right conditions, life could bloom from the chemical heart of matter itself. Yet, for every measured hypothesis, there surged forth a tide of wonder and fantasy. In the pages of novels, life was conjured in strange and secret ways. Mary Shelley's Frankenstein gave us the brooding vision of a scientist reanimating the dead, fusing flesh and lightning in a Gothic laboratory. The monster, stitched together from lifeless parts, becomes a mirror for our hopes and fears about creation. What are the limits of science? What does it mean to breathe life into mere matter? What, if anything, is sacred about the boundary between living and non-living? Shelley's tale, though a fiction, echoes deeper anxieties and desires. The idea that life might be created by accident, by design, or by some cosmic whim has haunted the human mind for generations. In the early 20th century, as telescopes reached farther and radio signals swept the heavens, new stories emerged. Science fiction pulsed with visions of panspermia, the hypothesis that life's seeds drifted through space, born on comets or meteorites, waiting to fall upon a fertile world. In worlds crafted by writers like H.G. Wells and Stanislaw Lem, life is neither unique nor miraculous. It is a phenomenon that might spring up anywhere under alien skies, in forms both wondrous and strange. Such stories, though they seem fanciful, are not idle dreams. They are the scaffolding upon which our scientific questions are constructed. The line between myth and method is not always sharp. Imagination often precedes investigation. When we picture the primordial earth, a world of churning oceans and lightning-laced skies, raw elements swirling in a chemical dance, we are, in a way, telling ourselves a new kind of origin myth, one shaped by the tools and discoveries of modern science. Still, even today, popular perceptions cling to the marvelous, the mysterious. For many, the origin of life remains a puzzle whose pieces are scattered across legend, laboratory, and the vast, cold reaches of the cosmos. Some envision the hand of a creator, meticulous and purposeful. Others imagine serendipity, a rare, beautiful accident in the crucible of early Earth. Still others look outward toward the galaxies and wonder if life is not an anomaly, but a cosmic inevitability, seeded wherever the right chemistry and conditions prevail. Every era has its own favored metaphors. In the language of the 21st century, we speak of code, of information, of self-replicating machines. The double helix of DNA, discovered in the mid-20th century, has become a symbol of life's profound complexity, a ladder of information, twined and compact, spelling out the instructions for existence. We marvel at the precision with which molecules arrange themselves, at the delicate choreography of proteins and enzymes, at the way a single cell can hold within it the potential for an entire organism. Yet beneath the technical language, the core question remains unchanged. How did the leap occur, from chemistry to biology, from chaos to structure, from the inanimate to the animate? It is a question that, despite centuries of study, still retains an aura of the miraculous. Science fiction, in its many guises, continues to explore the boundaries of this mystery. In some tales, life emerges from the digital ether, a consciousness born within the circuits of a supercomputer, or an intelligence awakening in the interconnected web of the Internet. In others, alien life evolves in the methane lakes of distant moons, or in the shadowed crevices beneath the icy crusts of Europa and Enceladus. Each story, no matter how wild, is a meditation on possibility. If life could begin here, why not elsewhere? If from simple matter, complexity and consciousness can arise, what might the universe be capable of? Popular perceptions are shaped too by the images and discoveries of our own age. The sight of extremophiles, bacteria thriving in boiling acid pools or in the crushing darkness of the ocean's floor, has expanded our sense of the possible. If life can endure such harshness, perhaps it is not so fragile, not so rare. Perhaps, given enough time and the right ingredients, life will always find a way to spark, to sustain, to evolve. At the same time, there is a persistent sense of awe at the improbability of it all. The odds, some say, are astronomical. Consider the complexity of a single protein, the dizzying intricacy of a living cell. How could such order arise from chaos? How could mere atoms, blind and indifferent, assemble themselves into creatures that see, feel, dream, and wonder? For every confident assertion, there is a counterpoint, a reminder that we are still standing at the threshold, peering into the darkness, searching for the faintest outline of understanding. Popular culture reflects this tension between hope and skepticism. Films and novels offer visions of laboratory triumph, of scientists mixing chemicals in flasks, watching as some vital spark leaps into being, and also cautionary tales, where life's creation leads to unintended consequences or to questions science cannot answer. In the public imagination, the laboratory and the temple are not so far apart. Both are places where the mysteries of life are approached with reverence and fear. Among scientists themselves, the story is more measured but no less wondrous. The study of abiogenesis, the process by which life arises naturally from non-living matter, has become a field of patient inquiry, rooted in chemistry, biology, and physics. The questions are precise. What molecules are needed? What conditions must prevail? Can we recreate the steps that might have led from a barren earth to a world teeming with cells? And yet, even as experiments inch closer to unraveling these mysteries, the popular imagination continues to soar. There is something irresistible about the idea that life could emerge from the lifeless, that order could bloom from chaos. It is perhaps the oldest story we know, a story not just of beginnings, but of becoming. We stand then at the edge of a vast and ancient mystery, guided by both the light of discovery and the shadows of myth. The origin of life is more than a scientific puzzle. It is a mirror in which we glimpse our own longing for connection, for meaning, for a place in the unfolding story of the cosmos. Tonight, as you listen to the gentle cadence of these words, let your thoughts wander through the corridors of time, where myth and reason flow together like rivers meeting at the sea. Picture the first storytellers huddled around fires, whispering of gods and monsters, of creation and chaos. Hear the voices of scientists, centuries later, peering into microscopes, mixing chemicals, pondering the secrets of the cell. Imagine the writers and dreamers, their pens dancing across the page, conjuring worlds where life is born in 1,000 strange and beautiful ways. All these voices, all these visions, are threads in a single tapestry, a tapestry that stretches from the dawn of existence to the farthest reaches of our own imaginations. Whatever the truth of life's beginnings, it is a story that belongs to all of us, a story written in the language of wonder. And so, as the night deepens and the world grows quiet, let us dwell a while longer in this place of possibility. Let the old questions linger, like distant stars glimmering at the edge of our knowing. For in the space between science and story, between what we dream and what we discover, the true prelude to life's origin continues to unfold, awaiting the next curious mind to ask, to imagine, to seek. Beneath the hush of darkness, the stage is set. The tale is only beginning. Somewhere, in the collision of atoms, in the dance of energy and chance, in the slow, patient turning of the earth, life's first secret stirs, silent, waiting, poised on the threshold between what is and what might be. In the dimness before dawn, as the world sleeps and the mind drifts toward half-remembered dreams, let us slip quietly into the ancient mystery at the heart of all living things, the threshold where the lifeless matter of the universe, for reasons still not fully grasped, became animate. This is the story of the chemical ballet, that took place in the silent eons before the first cell, the intricate dance that saw dust and water, gas and mineral weave themselves into the delicate tapestries of living form. The earliest Earth was a world of unrelenting violence and possibility. Volcanic eruptions split the crust, hurling molten rock and clouds of gas skyward. Lightning forked across heavy, carbon-rich skies. Oceans, still young, heaved with tides under the pull of a closer moon. In these roiling waters and steamy, mineral-laden shores, the raw elements of life, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, swirled endlessly, their atoms colliding, fusing, breaking apart, and recombining in countless permutations. But what exactly occurred in these crucibles of creation? How did the blind forces of chemistry conspire to build the first structures that could grow, replicate, and evolve, structures that would one day gaze back upon their origins with wonder? The question is as old as human curiosity, and it has never had a simple answer. The birth of life from non-life, known as abiogenesis, remains one of science's most profound riddles. Yet over the past century we have learned to peer into the heart of this mystery, guided by the flicker of experiments and the logic of molecular possibility. Let us begin with the most famous stage of this unfolding drama, the primordial soup. In the 1920s, scientists like Alexander Oparin and J.B.S. Haldane proposed that the early Earth's oceans were thick with dissolved organic molecules, a rich broth simmering with potential. According to their vision, energy from sunlight, lightning, and volcanic eruptions powered the assembly of simple molecules like methane, ammonia, and water into more complex organic compounds, amino acids, sugars, fatty acids, and nucleotides. This idea was put to the test in the early 1950s by Stanley Miller and Harold Urey. In their now legendary experiment, they sealed a mixture of methane, ammonia, hydrogen, and water in a glass flask, then sparked it with electrical discharges to mimic lightning. After just a week, the flask's waters had turned pinkish and cloudy. Analysis revealed the presence of several amino acids, the very building blocks of proteins. The Miller-Urey experiment seemed for a moment to open a direct path from the chemistry of the inanimate to the chemistry of life. Yet even in its triumph, the experiment raised new questions. For while it showed that amino acids and other simple organic molecules could form under plausible early Earth conditions, it left much unsaid about the next steps. How do such molecules assemble themselves into the elaborate architectures of living cells? How do strings of amino acids become functional proteins, or nucleotides form the double helix of DNA? The soup itself, however rich, is not enough. There must be a way to coax order out of chaos, to channel random collisions into the emergence of intricate, self-perpetuating systems. Here the tale grows more subtle, and the dance of chemistry more complex. Consider the nature of a living cell, a bustling, crowded metropolis of molecules, each with its role in metabolism, information storage, or structural support. Life as we know it depends on a triangular interplay of three kinds of macromolecules: proteins, nucleic acids, and lipids, each made from simpler subunits, each possessing the uncanny ability to assemble with high specificity and efficiency. The leap from mere mixture to organization is a puzzle that has inspired a host of theories, each seeking to explain how structure and function could arise spontaneously from the jumbled ingredients of the prebiotic world. One line of thought focuses on the properties of membranes. In water, certain molecules, fatty acids for instance, naturally self-assemble into spherical shells called vesicles, their hydrophilic heads facing outward, their hydrophobic tails tucked safely inside. These primitive bubbles could serve as the first containers separating the chemical contents within from the vast, indifferent ocean outside. Inside such vesicles, molecules might concentrate, react, and evolve in relative isolation. The first compartments of life, formed not by conscious design but by the physics of water and oil, may have provided the stage upon which further complexity could unfold. Yet compartments alone do not a cell make. There must also be a way to store information and pass it on, to encode the instructions for self-replication. Here, the story turns to the remarkable molecules known as nucleic acids, especially RNA. The RNA world hypothesis proposes that, before DNA and proteins, life was built on the versatile backbone of ribonucleic acid. RNA is a molecule that can both store genetic information, like DNA, and catalyze chemical reactions, like a protein enzyme. In the crucible of the early Earth, simple chains of RNA might have formed spontaneously. Some of these chains could fold into shapes capable of speeding up their own replication, or the assembly of other crucial molecules. Over time, those that were better at making more of themselves, or at helping their fellow molecules do so, would become more common. A primitive form of natural selection, playing out long before the first true cell. But even this elegant idea is riddled with uncertainties. The spontaneous formation of long, information-rich RNA molecules in the wild is exceedingly improbable, given the instability and complexity of their chemical bonds. Some scientists propose that simpler molecules, perhaps earlier cousins of RNA, served as stepping stones. Others suggest that mineral surfaces, clay perhaps, or iron pyrite, helped guide the assembly of nucleic acids, acting as scaffolds that held the right ingredients close together. From another angle, there is the metabolism first hypothesis. Rather than focusing on information storage, this theory asks whether cycles of chemical reactions, metabolic networks, could have arisen spontaneously, fueled by energy sources such as geothermal heat or sunlight. On the slopes of ancient hydrothermal vents, perhaps simple molecules could enter into repeating cycles of reaction, each step making the next more likely. Over time, these cycles might grow more elaborate, incorporating new molecules and pathways until they became self-sustaining, capable of growing, dividing, and evolving. Some proponents of this view point to the remarkable similarities between modern cellular metabolism and the chemistry of certain rocks and minerals. In deep-sea vents, for example, iron and sulfur compounds can drive the formation of organic molecules from carbon dioxide and hydrogen in a process not unlike the core of the metabolic cycles found in living cells today. These mineral-driven reactions might have been the seeds from which life's elaborate chemistry sprouted. As we wander deeper into these thickets of theory, it becomes clear that the boundary between living and non-living is not so much a wall as a gradually rising slope. At what point does chemistry become biology? Is it when a molecule can copy itself, albeit imperfectly? When compartments form, protecting their contents from dilution and destruction? When networks of reactions can sustain themselves, feeding and growing and dividing with something like purpose? The answers are elusive, and perhaps in some ways forever beyond our reach. For the story of life's beginnings is written in ephemeral ink on a planet that has been remade countless times by erosion, subduction, and catastrophe. The rocks that might have preserved traces of these earliest experiments are long since gone, their secrets ground to dust and scattered to the wind. Still, the search continues. In laboratories around the world, glass flasks bubble and shimmer with mock primordial seas. Scientists mix and match ingredients, adjusting temperature, pH, and mineral content, seeking the conditions that might coax inanimate molecules into ever more lifelike behaviors. Some experiments have shown that simple fatty acids can indeed form stable vesicles, that short strands of RNA can catalyze their own replication, that certain mineral surfaces can promote the assembly of key biological molecules. Yet, each success raises a new question. each advance revealing further layers of complexity. The problem of chirality, for example. Amino acids and sugars come in two mirror image forms, like left and right hands, but life uses only one version of each. How did this preference arise from a world where both forms should be equally common? Or the challenge of information? Even the simplest modern cell contains thousands of genes, each encoding intricate instructions. How could such complexity emerge from a handful of chance-assembled molecules? To these questions, there are few definitive answers. The story of abiogenesis is not a single thread, but a tapestry woven of many strands, each plausible, each incomplete. Some scientists propose that life began not once, but many times, in scattered pockets across the globe, with only the most robust forms surviving to give rise to all later life. Others suggest that the critical spark might have come from elsewhere, delivered by meteorites bearing organic molecules forged in the cold darkness of space, a hypothesis known as panspermia. Even if true, this only pushes the question of origins further back to other worlds and other times. What we know with growing certainty is that the boundary between chemistry and life is not as sharp as once imagined. Life is not a sudden leap, but a slow, meandering ascent up a slope of increasing complexity and order. Somewhere along that slope, simple molecules learn to join hands, to build structures larger and more intricate than themselves. Networks of reaction emerged, first fragile, then increasingly robust. Compartments formed, protecting their molecular cargo from the chaos outside. Information began to accumulate, encoded in sequences of bases and chains of amino acids, passed down from molecule to molecule, and eventually from cell to cell. And so, in the primeval world, a quiet revolution unfolded. The chemical ballet, at first random and directionless, began to settle into recognizable steps. Patterns emerged, repeated and refined by the logic of self-assembly and the pressures of selection. The inanimate, given time and the right conditions, became animate. Yet even as we reconstruct this story in the laboratory and the mind's eye, we must remember the limitations of our understanding. The Earth we know today is but a pale echo of its ancient self. The true conditions of the early planet, its oceans, its atmosphere, its mineral wealth, remain matters of debate. Each experiment, meticulously designed though it may be, is but a shadow of the vast and unpredictable world in which life first arose. Still, we can marvel at what we do know, that from the tumult of the early earth, order emerged. That the laws of chemistry, given enough time and the right environment, are capable of astonishing creativity. That the difference between the living and the non-living is not so much a matter of substance, but of organization, a difference of arrangement, interaction, and above all, of persistence across time. And so, as the night deepens and the mind drifts, we are left with the image of the ancient world, a place of storms and silence, of simple molecules moving endlessly in the dark, drawn together by the subtle, inescapable pull of chemistry. Some would pass on, dissolved and forgotten. Others, by chance or by law, would find themselves caught up in the dance, forming chains, networks, bubbles, and loops. In those moments, however fleeting, the first seeds of life were sown. What came next is a story of endless transformation, of molecules learning to work together, to harvest energy, to build the machinery of growth and division. The dawn of metabolism, the rise of genetic codes, the first glimmers of evolution. These are chapters yet to be told as our journey continues, deeper into the unfolding mystery of life. If you listen closely, in the silence of late hours, when the hum of daily life fades, you may catch an echo, the faint, persistent question that has haunted thinkers for centuries. How did the story of life truly begin? The question is ancient, and the search for its answer has woven a long, intricate thread through the fabric of human curiosity. Tonight we pick up that thread, following its twists and tangles not through speculation, but through the work of hands, the invention of tools, and the boldness of experimenters who dared to recreate the world as it might once have been. In the dim glow of oil lamps and under the stark light of modern laboratories, generations of scientists have summoned the primordial world into glassware and steel, seeking to coax life's first breath from the inanimate elements. But before beakers and electrodes, before even microscopes, there were simply questions and the power of observation. The earliest thinkers, philosophers of the ancient world, gazed at ponds and imagined the spontaneous animation of mud, the miraculous birth of wriggling eels from riverbanks, the sudden appearance of flies around meat left in the sun. It seemed to them that life was an emergent property of the earth itself, a notion that would persist for centuries, woven into the very language of creation myths and natural philosophy. Yet as centuries turned, those old beliefs began to fray. The Renaissance, with its zeal for experiment and evidence, brought with it the first glimmers of skepticism. Francesco Redi, a physician of the 17th century, took up the challenge. He placed meat in jars, some sealed, some open, some covered with fine gauze, and watched. The result, so simple and so profound, was that only open jars teemed with maggots. Life, Redi showed, did not spring unbidden from dead flesh. It arrived on the legs of flies. A single, elegant experiment had sundered the dogma of spontaneous generation for larger creatures. But the question of how the first life arose, in a world without flies or jars or even flesh, remained untouched. The centuries that followed would be marked by the gradual accumulation of tools, lenses polished to perfection, vessels crafted with exquisite care, scales sensitive enough to weigh the invisible, and, eventually, machines capable of probing the very architecture of molecules. Each new tool opened another window onto the mysteries of life's beginnings. The microscope, that magical extension of the human eye, brought the invisible world into view. With it, the tangled forms of protozoa and bacteria, Leeuwenhoek's animalcules, were revealed. Suddenly, the world teemed with hidden life, and the possibility that life's origin might lie in the realm of the minuscule became plausible. Still, for centuries, the leap from chemistry to biology, from lifelessness to animation, was a chasm unbridged. It was in this context, in the first half of the 20th century, that the primordial thread was picked up afresh. The physicist-turned-biologist Alexander Oparin, working in the Soviet Union, and the British scientist J.B.S. Haldane, working independently, each proposed a vision that life could arise through the gradual assembly of organic molecules from simpler compounds, given the right conditions. They pictured a young Earth, its atmosphere thick with methane, ammonia, water vapor, and hydrogen, and hypothesized that energy, perhaps lightning, perhaps ultraviolet light, could drive these simple gases to form the building blocks of life. These ideas were bold, but they remained for the moment in the realm of theory. What was needed was a way to test them, to summon the ancient Earth into the laboratory. And so, in 1952, a young graduate student named Stanley Miller, under the guidance of Harold Urey, constructed a device that would echo through the history of science. Imagine a glass apparatus, looping and twisting like some alchemical instrument from a medieval dream. In one flask, Miller placed water, symbolizing the ancient oceans. Above it, he allowed a mixture of methane, ammonia, and hydrogen to circulate, his recreation of the primordial atmosphere. Electrodes arced inside, crackling with simulated lightning. The cycle churned, water vapor rising, condensing, raining back down. After days of this artificial tempest, the once clear water had turned cloudy and pinkish. Analysis revealed the presence of amino acids, the very monomers from which proteins and thus life are constructed. This was no mere trick of chemistry, but a demonstration that, under plausible prebiotic conditions, the fundamental ingredients of life could assemble themselves. The Miller-Urey experiment became an icon, its image etched into textbooks and imaginations alike. Yet, as with all great experiments, it raised as many questions as it answered. If amino acids could form so readily, could other building blocks, nucleotides, sugars, lipids, also emerge from such conditions? And how might these molecules have organized themselves into something with the properties of life? The decades that followed saw a proliferation of experiments, each a variation on Miller and Urey's theme. Scientists bombarded mixtures of gases with ultraviolet light, simulated volcanic eruptions, and even recreated the high-pressure environments of hydrothermal vents at the bottom of the sea. Each new approach revealed further complexity. Organic molecules could indeed form in many scenarios, sometimes even more easily than Miller and Urey had demonstrated. In the cold darkness of space, on interstellar dust grains, and on meteorites fallen to Earth, amino acids and other organic compounds have been found, suggesting that the ingredients for life are not unique to our planet. Still, the leap from chemistry to biology is vast. The formation of amino acids is but the first page of the story. To proceed, we must consider how molecules, once formed, might assemble into more complex structures, how the first self-replicating entities arose, and how they might have harnessed energy and information to persist and evolve. Here, the tools of molecular biology come to the fore. The development of chromatography, electrophoresis, and spectroscopy allowed scientists to tease apart complex mixtures, to identify fleeting intermediates, and to track the fate of atoms as they journeyed through chemical reactions. With the advent of radioisotopes, researchers could label molecules, following them like invisible ink through the labyrinth of prebiotic chemistry. Each experiment, each new method, revealed another twist in the thread. One avenue of exploration focused on the assembly of membranes. For life as we know it, the cell is the basic unit, and the cell is defined by its boundary, a membrane of lipids that separates inside from outside, self from environment. Could such structures form spontaneously? In the 1960s and 70s, researchers discovered that fatty acids, when placed in water, could self-assemble into vesicles, tiny hollow spheres akin to primitive cells. These vesicles could encapsulate other molecules, creating a microenvironment, a first step towards cellularity. Even more tantalizing, under certain conditions, these protocells could grow and divide, mimicking the behavior of living cells. Yet a cell, even a primitive one, is more than a bag of molecules. It is a machine for processing information, for storing instructions, and transmitting them across generations. Here, the story turns to nucleic acids, the mysterious carriers of genetic information. The discovery of the double helix by Watson and Crick in 1953 unveiled the language of life, but it also posed a riddle. Could such a molecule form under prebiotic conditions? Could RNA, or its precursors, arise spontaneously, and if so, could they replicate themselves? To probe these questions, scientists devised ever more ingenious experiments. Some mixed simple chemicals, hydrogen cyanide, formaldehyde, and others, under conditions mimicking early Earth, and found that with patience, sugars and nucleobases could emerge. The path was not straightforward, often requiring cycles of wetting and drying, or the presence of mineral catalysts. Yet, with every success, the plausibility of a RNA world, a stage in which RNA molecules both stored information and catalyzed their own replication, became more compelling. The tools grew ever more refined. Mass spectrometers, able to weigh single molecules with exquisite precision, revealed the presence of fleeting intermediates, while atomic force microscopes allowed scientists to visualize the very shape of protopolymers as they twisted and folded. Computers, too, became indispensable tools, able to model the chaotic dance of molecules and predict which pathways might be plausible amidst the tumult of a young planet. Some experiments sought to recreate not just molecules, but the very processes of evolution. In the late 20th century, researchers began to evolve molecules in the laboratory, setting up competitions in test tubes where RNA sequences could mutate and replicate, with the fittest sequences dominating over time. These directed evolution experiments revealed that, even in the absence of cells or enzymes, molecules could adapt and improve, provided the right conditions and selection pressures. Beyond chemistry, physicists and geologists joined the quest. They measured the ancient rocks of Greenland and Australia, seeking chemical signatures, subtle ratios of carbon isotopes, or the presence of certain minerals that might betray the activities of the earliest life. In ancient zircons, some found hints of water dating back over 4 billion years, suggesting that the stage for life's emergence was set almost as soon as the planet cooled. The search has even reached beyond Earth. Robotic explorers, outfitted with spectrometers and chromatographs, have tasted the atmosphere of Titan, drilled into the icy crust of Enceladus, and sifted the dust of Mars, searching for organic molecules or chemical imprints of life. Meteorites, too, have been scrutinized, revealing not only amino acids, but exotic sugars and complex hydrocarbons formed in the cold dark of interstellar space. Throughout all these endeavors, the thread that binds them is one of ingenuity, a willingness to imagine, to build, and to test. The tools and experiments are themselves a kind of evolution, each generation refining the work of the last, adapting to new ideas and new evidence. And always there is the sense that we are peering backwards in time, summoning the ancient Earth, molecule by molecule, into the present. Yet, for all our cleverness, the origin of life remains an enigma, its secrets hidden not just in the chemistry of molecules, but in the improbable dance of chance and necessity. We can recreate the conditions, assemble the ingredients, and even coax them into ever more lifelike behaviors. But the leap from non-life to life still shimmers just out of reach, a threshold we glimpse but have yet to cross. Still, the work goes on. New tools are forged, microfluidic devices that can simulate the cycles of drying and wetting on early Earth, lasers that can probe the structure of molecules as they form and break, artificial intelligence that can sift through the vastness of chemical space to predict new pathways. Each experiment is a question posed to the universe, each result an answer that begets more questions. The thread stretches onward through the laboratories of today and into the mysteries that remain. Somewhere, perhaps, in the interplay of molecules and energy, of chance and necessity, lies the secret that will finally reveal how the silent Earth quickened and began to dream. For now, we watch, we listen, and we wait, tracing the patterns of the past with all the tools at our disposal, hoping that the next experiment may yet bring us closer to the moment when chemistry became life. And as the night deepens, the primordial thread, unraveled and rewoven by generations of seekers, draws us onward still, toward the possibilities that lie ahead, and the new frontiers that beckon just beyond the horizon of knowledge. There is a hush that settles in the mind when one contemplates the origin of life, a silence not of ignorance, but of reverence. It is the hush that fills the ancient forests in the hour before dawn, the hush that lingers above the deep ocean trenches, and the hush that envelops the stars as they wheel in their stately dance. In this silence, the questions that have echoed through human thought for millennia seem to gather, awaiting the faintest spark that might illuminate their answers. How did life arise from the lifeless? What alchemy transformed the inert dust of the cosmos into the vibrant, self-aware tapestry that is living matter? And, perhaps most hauntingly, what does it mean for us, creatures of stardust, to be conscious of our own beginnings? As we turn our attention to these questions, let us drift gently among the eddies of thought and discovery that ripple through the story of life's origins. The tale is vast and unfinished, a symphony in which each movement reveals new motifs, new harmonies, yet never quite resolves. We are drawn again and again to the threshold of the unknown, peering with awe and humility into the wellspring from which all living things flow. At the heart of this mystery lies the transformation of matter, simple, unadorned atoms shaped in the furnaces of stars and hurled across the gulfs of space, finding themselves upon a young, restless planet. Carbon, hydrogen, oxygen, nitrogen, these elemental players, once scattered and alone, converge in the primordial seas, carried by the dance of water and wind. Lightning splits the sky, the sun's rays warm the surface, and the great engines of chemistry begin their work. Bonds form, break, and reform in endless permutation, exploring every avenue of possibility. The question that has haunted generations of scientists is, at what point does this chemical exuberance become something more? What is the dividing line between the molecular and the living? The answer, elusive and shifting, remains the subject of passionate debate. Some see it in the emergence of self-replicating molecules, chains of nucleotides that carry, imperfectly, the instructions for making more of themselves. Others see it in the birth of metabolism, the web of reactions that captures energy and builds complexity. Still others insist that life begins with compartmentalization, the drawing of a fragile membrane, a boundary that separates the self from the world. It is tempting, as we examine these theories, to search for a single moment, a definitive threshold crossed by the first living thing. But nature, it seems, does not adhere to our desire for neat boundaries. The birth of life was likely a gradual dawning, a slow accretion of functions and features, each making the next more probable. In the muddy shallows of the ancient earth, droplets of fatty acids may have gathered, encasing primitive genetic materials and catalytic molecules. Within these simple vesicles, cycles of replication and selection could have played out, driven by the ceaseless churn of the environment. With each turn of the tide, with each fluctuation in temperature and chemistry, some combinations would have faltered and vanished, while others persisted ever so slightly better at surviving and reproducing. Over uncounted generations, these lucky arrangements would converge on greater complexity and resilience. The line between non-life and life would blur, the difference growing not from a single leap, but from countless small steps. This gradualist view is supported by the tantalizing diversity we find among the simplest forms of life today. Some bacteria thrive in boiling acid, others in the cold darkness beneath Antarctic ice. Some build their bodies from the most basic of ingredients, while others beg, borrow, or steal from their neighbors. Life's ingenuity, its capacity to adapt and diversify, speaks of an origin story, not of sudden brilliance, but of patient, relentless experimentation. Yet, for all that we have learned, the mystery remains profound. We have coaxed simple peptides and nucleotides to form in our laboratories, sparked into being by simulated lightning or cosmic radiation. We have watched lipid bubbles assemble themselves in water, and we have glimpsed autocatalytic cycles, networks of molecules that sustain and replicate their own existence. But no one has yet witnessed the full emergence of life from non-life. The spark that ignited the symphony of existence remains hidden, perhaps lost in the deep history of our planet, or perhaps still waiting to be discovered in some humble experiment. And so we are left with the profound realization that life's origin may not be a singular event, but a process that is, under the right conditions, as natural as the falling of rain or the blooming of a flower. If so, then the implications are staggering. The universe, with its billions of stars and its uncounted worlds, may be rich with the potential for life. The chemistry that gave rise to us is not unique to Earth. It is written in the language of the cosmos. Everywhere that water flows, everywhere that energy stirs and complex molecules gather, there may be the possibility, however faint, of life awakening. This thought, binds us to the universe in a way that is at once humbling and exhilarating. We are not separate from the world, nor from the stars. We are their children, shaped by the same forces that shaped the rivers and the mountains, the clouds and the comets. Our very breath, the beating of our hearts, the thoughts that flicker behind our eyes, all are the legacy of cosmic processes set in motion billions of years before we were born. It is here, in this sense of kinship, that the story of life's origin acquires its deepest resonance. For to understand our beginnings is not only to unravel a scientific puzzle, but to glimpse our place in the unfolding story of the universe. The boundaries that seem to separate us from the rest of existence dissolve, revealing a continuity that stretches from the first atoms to the most complex minds. Consider for a moment the journey of a single carbon atom. Forged in the fiery heart of a dying star, it drifted through interstellar space, caught eventually in the gravity of a young forming planet. Locked for eons in stone or sea, it was freed by the restless churning of Earth's surface, taken up into a molecule of methane, or perhaps a leaf of green. Through the slow work of time, it passed from microbe to fish, from tree to mammal, until at last it became a part of you, a thought, a breath, a heartbeat. The story of that atom is the story of us all, a reminder that we are woven from the same fabric as all things. Yet, as we reflect on this, another layer of wonder unfolds. For life, once begun, does not merely persist, it transforms. The earliest living things, simple and blind, gave rise to beings of extraordinary complexity and awareness. Through the long history of evolution, life learned to sense light, to move, to remember, to dream. The unbroken chain that stretches from the first replicating molecules to the consciousness that ponders its own origins is a testament to the creative power of nature. This creativity is not random, nor is it predetermined. It is a dance of chance and necessity, of trial and error, of adaptation and selection. The great tree of life, with its branching forms and its myriad leaves, is shaped by the interplay of order and chaos. And within this tree we find not only the record of our past, but the seeds of future possibility. In this light, the search for life beyond Earth becomes not just a scientific endeavor, but a quest for connection. If the principles that gave rise to us are universal, then the cosmos may be teeming with other symphonies, other forms of life, other stories unfolding in the vastness of space. The discovery of even the simplest microbe on a distant world would be a revelation, a confirmation that we are not alone in the great unfolding of existence. But even if we never find such life, the implications remain profound. For in seeking to understand life's origins, we are compelled to look both outward and inward. Outward to the stars and the planets, to the chemistry that unites the universe. Inward to the patterns of thought and feeling that define our own existence. The questions we ask of the cosmos become, in the end, questions we ask of ourselves. What does it mean to be alive? Where do we draw the boundaries of self and other, of mind and matter? How do we find meaning in a universe that is, by all appearances, indifferent to our desires? These are questions that science alone cannot answer, for they belong as much to philosophy and poetry as to experiment and observation. And yet, the pursuit of understanding, the longing to know where we come from and what we are, is itself a testament to the power and beauty of life. There is a gentle irony here, that we, creatures of dust and water, should be capable of contemplating our own origins. The atoms that make up our brains, our hands, our hearts, were once part of lifeless rock and gas. Through the patient unfolding of natural law, they have become part of a mind that can ask, "Why am I here?" In this sense, the universe has become conscious of itself, at least in this small, fleeting corner of space and time. As the night deepens and the world grows still, the story of life's origins continues to unfold. New discoveries await, new mysteries beckon. In the laboratory, in the field, in the silent meditation of thought, we reach toward understanding, even as the horizon recedes before us. The symphony of existence plays on, each note resonant with possibility. And so, as we drift in the quiet currents of reflection, we find ourselves caught between wonder and humility. We are the heirs of a cosmic drama, participants in a story that began long before we arrived and will continue long after we are gone. Our lives, brief and fragile, are nonetheless part of something vast and enduring. Somewhere, perhaps, in the depths of a distant ocean, or beneath the ice of a far-off moon, the same chemistry that gave rise to us is at work, weaving new possibilities. The universe is not finished. Its creativity is boundless. And so we listen, with patience and hope, for the next movement in the symphony of existence. A movement we may one day hear, or perhaps only imagine, as we close our eyes and dream of beginnings without end. As our journey through the origins of life gently drifts to a close, like a comet tail fading softly into the hush of space, may your thoughts wander peacefully through the quiet wonder of beginnings unknown. Rest easy beneath the vast cosmos, and when you're ready to dream again, return for more whispered mysteries from the stars.